Everything you see tonight will disappear forever. You feel perfectly still right now. That's the universe's cruelest illusion. Tonight we're discovering how distant galaxies race away faster than light itself. Why our cosmic neighbors vanish beyond reach. And why this cosmic exodus changes everything. Before we dive into this expanding cosmos, drop a comment about what fascinates you most about space. If these cosmic journeys spark your curiosity, consider subscribing for more. Astronomers once believed the universe stood perfectly still. Galaxies hung in space like monuments frozen in time. Then they examined starlight more carefully. Everything changed. Light acts like a cosmic messenger carrying secrets about motion. When something moves away from you, its light gets stretched out. Think of how a siren sounds lower as an ambulance drives away from you. Light does the same thing. It shifts toward the red end of the spectrum. Scientists call this effect redshift. It's simply light getting stretched when its source moves away. Edwin Hubble made the startling discovery. He found that nearly every galaxy in the sky showed this red signature. The farther away a galaxy sat, the redder its light appeared. This pattern meant something impossible by old thinking. The entire universe was expanding. Space itself stretched like a balloon being inflated, carrying galaxies along for the ride. We'd been living inside a cosmic explosion without realizing it. Hubble measured hundreds of galaxies. He plotted their distances against how fast they moved away. What he found shocked the scientific world. The relationship formed a perfect straight line. Galaxies twice as far moved twice as fast. Triple the distance meant triple the speed. This wasn't random motion. It was orderly universal expansion. Scientists named this pattern Hubble's law. It's a simple rule that governs the entire cosmos. The numbers revealed something incredible. Distant galaxies race away at thousands of kilometers per second. That's faster than anything humans have ever built. Every region of space expands at exactly the same rate. From any galaxy's perspective, all others appear to be fleeing away. We're not at the center of this expansion. We're witnessing it from our particular spot in space. The universe behaves like everyone is running away from everyone else. Most people imagine the universe expanding like a bomb going off, matter flying outward through empty space. That picture is completely wrong. The universe doesn't expand into anything. Space itself grows larger. Imagine dots painted on a balloon. As you inflate it, the dots move apart not because they're flying through the balloon, but because the balloon itself stretches. This means there's no center to the expansion. No edge either. Every point in space sees the same thing happening. Everything else moving away. Space expansion affects every distance in the universe. The gap between galaxies grows. Even the space between atoms would expand, except stronger forces hold matter together locally. 13.8 billion years ago, all of space was compressed into an infinitely small point. Then space itself began growing, and it's been expanding ever since. This expansion creates all the room that galaxies, stars, and planets occupy today. In the 1960s, scientists discovered something extraordinary. The entire universe glows with faint microwave radiation. This glow comes from every direction in space. This radiation is the afterglow of the Big Bang itself. When the universe was very young, it was incredibly hot, hotter than the core of any star. As space expanded, this heat got stretched and cooled. Scientists call this the cosmic microwave background. It's basically the heat left over from when the universe was born. The temperature of this background radiation is nearly absolute zero, just a few degrees above the coldest possible temperature. but it's perfectly uniform across the entire sky, proving the universe started from a single, incredibly hot beginning. This discovery confirmed that universal expansion isn't just happening now. It's been going on for almost 14 billion years, cooling the universe down from its fiery birth to the cold cosmos we see today. If the universe is expanding now, what happens if you run time backward? All the galaxies get closer together. All of space shrinks down. Keep running the clock backward, and eventually everything, all matter, all energy, all space itself, gets squeezed into a single point. Scientists call this the Big Bang. The Big Bang wasn't an explosion in space. It was the beginning of space itself. Before this moment, there was no before. Time itself started ticking. This means the universe has a birthday. Every galaxy, every star, every atom traces back to that single moment when space and time began. The evidence for the Big Bang comes from multiple sources. The expansion of space, the cosmic background radiation, and the types of elements we find throughout the universe all point to the same conclusion. Our entire cosmos emerged from an unimaginably dense and hot beginning nearly 14 billion years ago. Scientists can calculate exactly when the Big Bang happened. They do this by measuring how fast the universe expands today, then calculating backward to find when everything was squeezed together. The expansion rate tells us how much time has passed since space began growing. It's like watching a movie in reverse. You can figure out when it started. Current measurements show the universe is 13.8 billion years old. That's the age of space and time themselves. This age puts everything in perspective. Human civilization has existed for only a tiny fraction of cosmic time. Even our solar system formed relatively recently, just 4.5 billion years ago, when the universe was already 2/3 of its current age. The universe's finite age means we can only see a limited portion of it. Light from the most distant objects has been traveling toward us since near the beginning of time itself. In the 1990s, astronomers made a shocking discovery. They expected the expansion of the universe to be slowing down. Gravity should pull everything back together, right? Instead, they found the opposite. The expansion is accelerating. The universe grows larger at an ever-increasing rate. Something is pushing space apart with tremendous force. Scientists call this mysterious influence dark energy, but they don't know what it is. Dark energy makes up about 70% of everything in the universe. It's completely invisible and doesn't interact with ordinary matter. We only know it exists because it's stretching space faster and faster. This acceleration has profound consequences. It means distant galaxies will eventually disappear beyond our reach forever. The universe is entering a phase of eternal expansion that will leave our local neighborhood increasingly isolated. The universe might be infinite, but we can only see a finite portion of it. Light takes time to travel, so there's a maximum distance from which light has had time to reach us. Scientists call this boundary the observable universe. It's like a sphere centered on Earth, beyond which we cannot see anything. Not because there's nothing there, but because light from those regions hasn't had time to arrive yet. This boundary sits about 46 billion light years away in all directions. That might seem to contradict the universe's age of 14 billion years, but remember, space itself has been expanding while light traveled toward us. The observable universe contains everything we can ever hope to detect. Beyond this boundary lie regions of space that remain forever hidden from our view. As the universe ages, this boundary slowly grows larger. We can see a bit farther each year, but with accelerating expansion, many galaxies we see today will eventually disappear beyond this cosmic horizon. In an expanding universe, the simple question, how far away is that galaxy, becomes impossibly complicated. Distance changes while you're measuring it. Consider a galaxy that's currently 10 billion light-years away. The light we see from it started traveling when the universe was much smaller. Back then, that galaxy was actually much closer to us. Scientists use multiple definitions of distance. There's the distance light traveled to reach us, the distance the galaxy was when the light started its journey, and the distance the galaxy is right now. These three numbers can be dramatically different. A galaxy whose light took 10 billion years to reach us might currently be 20 billion light-years away. This confusion reveals something profound about space itself. In an expanding universe, distance becomes a fluid concept. The very fabric of space grows between objects while light travels through it. If expansion continues accelerating, the universe faces a lonely future. Distant galaxies will eventually move away faster than light can travel. This means their light will never reach us. They'll fade from view permanently. Future astronomers might see only our local group of galaxies, with everything else vanished into darkness. The process has already begun. Some galaxies we can see today are already unreachable. If we tried to send a signal to them, it would never arrive. Within 100 billion years, nearly all galaxies will disappear from view. Our descendants will inhabit a universe that appears almost empty. Just a few nearby galaxies surrounded by infinite darkness. This cosmic isolation represents the ultimate consequence of accelerating expansion. The universe will become a collection of island galaxies, each cut off from all the others by the ever-growing space between them. Multiple independent lines of evidence all point to the same conclusion. The universe is expanding and has been since the Big Bang. The redshift of distant galaxies provides direct evidence. The cosmic background radiation shows us the afterglow of creation. The ages of the oldest stars match the calculated age of the universe. Even the chemical composition of stars supports expansion. The amounts of hydrogen and helium throughout the cosmos match exactly what the Big Bang theory predicts. No competing theory explains all these observations. Universal expansion isn't just one scientist's idea. It's the only explanation that fits everything we see. This convergence of evidence represents one of science's greatest triumphs. From simple observations of starlight, humans discovered the origin and fate of everything that exists. We live in an expanding cosmos that began with the Big Bang and will continue growing forever, carrying us on a journey through space and time that started nearly 14 billion years ago. Nothing travels faster than light. This isn't just a rule. It's the universe's ultimate speed limit, and this limit creates the most important boundary in all of existence. Light from the most distant objects has been racing toward us since the universe began. But even light needs time to cross cosmic distances. Since the universe is only 13.8 billion years old, light has only had that much time to reach us. This creates what scientists call the observable universe. It's like a sphere surrounding Earth, marking the farthest distance from which light has had time to arrive. The speed of light seems incredibly fast. It could circle Earth 7 times in 1 second, but on cosmic scales, it's frustratingly slow. The nearest star beyond our Sun takes over 4 years for its light to reach us. This speed limit means we can never see the entire universe. There are regions of space so far away that their light hasn't had time to complete the journey to Earth. The universe might extend infinitely, but we're trapped inside a bubble of visibility created by light's finite speed. Beyond the observable universe lie vast regions we cannot detect, not because they're empty or dark, but because their light is still traveling toward us through space. Think of it like messages sent from distant cities. If someone in Tokyo sends you a letter today, you won't receive it immediately. The letter needs time to travel. In the same way, light from the most distant regions of space is still en route to Earth. Some galaxies exist so far away that their light started the journey before Earth even formed. That light is crossing empty space right now, carrying images of ancient cosmic events we've never seen. Scientists call this the light travel time problem. We don't see objects as they are now. We see them as they were when their light began the journey. This delay creates a fundamental limit to cosmic knowledge. There are countless galaxies, stars, and cosmic events happening right now that we cannot observe. Their light simply hasn't had enough time to cross the enormous distance of space and reach our telescopes. Here's where cosmic distances become truly mind-bending. The observable universe extends much farther than you'd expect from simple calculations. If the universe is 13.8 billion years old, you might think the observable universe stretches 13.8 billion light-years in every direction. But that's wrong. It actually extends about 46 billion light-years. This happens because space itself expands while light travels through it. Imagine an ant walking across a balloon while you inflate it. The ant's journey becomes much longer than it would be on a stationary surface. Space expansion stretches the path that light travels. A galaxy that was relatively nearby when it emitted light might now be incredibly far away by the time that light reaches us. This expansion effect means the observable universe grows larger than the simple speed of light calculation would suggest. We can see objects that are now much farther away than light could travel in the age of the universe, because space itself has been stretching during the entire journey. The cosmic microwave background represents the oldest light we can ever observe. It's the afterglow from when the universe first became transparent, about 380,000 years after the Big Bang. Before this moment, the universe was completely opaque. Free electrons scattered light in all directions, making space as foggy as thick clouds. No light could travel far without hitting something. Then the universe cooled enough for atoms to form. Suddenly, light could travel freely through space for the first time. This moment, called recombination, created the cosmic background radiation we detect today. This ancient light marks the absolute boundary of direct observation. We cannot see anything that happened before recombination because no light from earlier times can reach us. The cosmic microwave background acts like a wall of ancient light surrounding us at the edge of the observable universe. Beyond this wall, we enter a realm of cosmic darkness that no telescope will ever penetrate. Everything earlier than this moment remains forever hidden from direct view. Every observer in the universe sees their own unique version of the cosmos. Your observable universe is different from an alien's observable universe in a distant galaxy. This happens because each observer sits at the center of their own light bubble. Light reaches them from different regions of space, creating a personalized view of cosmic history. An observer in the Andromeda Galaxy sees Earth's region of space as it was 2.5 million years ago. Meanwhile, We see Andromeda as it appeared 2.5 million years in its past. Scientists call this the relativity of cosmic horizons. There's no single, universal view of the cosmos, only individual perspectives from different locations. This means vast regions of the universe exist that no two observers share in common. What you can see from Earth might be completely invisible to an alien civilization elsewhere, and vice versa. Each cosmic address creates its own unique window into the universe's history and structure. The observable universe is about to enter a dark age. Accelerating cosmic expansion will eventually make distant galaxies disappear from view forever. As expansion speeds up, more and more galaxies will cross a critical boundary. They'll move away so fast that their light can never catch up to us. Once this happens, they fade from visibility and vanish into darkness. This process has already begun. Some galaxies we observe today are already unreachable. If we tried to send them a signal, it would never arrive. They're racing away too fast. Within 100 billion years, nearly every galaxy beyond our local neighborhood will disappear. Future astronomers will inhabit a universe that appears almost empty. The observable universe of the future will be much smaller than today's. Instead of seeing billions of galaxies, our descendants might observe only a handful of nearby objects surrounded by infinite darkness. Accelerating expansion is slowly erasing the cosmic vista that we take for granted. The universe has two different types of horizons that work in opposite directions. One limits what we can see from the past. The other limits where we can send signals in the future. The particle horizon marks the boundary of regions whose light has had time to reach us. We can observe events from these regions, but only as they happened in the distant past. The event horizon marks the boundary of regions we can still influence with signals sent today. Beyond this boundary, our messages will never arrive, no matter how long we wait. Here's the strange part. These two boundaries don't match up. Some galaxies exist within our particle horizon, so we can see them, but beyond our event horizon, so we can never communicate with them. This creates a cosmic asymmetry between past and future. We can receive information from regions we can never reach. The universe allows us to look but not touch, to observe but not interact, creating a fundamental separation between knowledge and influence. Scientists can make educated guesses about regions beyond our cosmic horizon. They do this by studying patterns in the observable universe and extending them outward. The cosmos shows remarkable uniformity in all directions we can see. Galaxy clusters, cosmic structure, and even the background radiation appear virtually identical whether we look north, south, east, or west. This uniformity suggests that regions beyond our horizon probably look similar to what we observe. The same physical laws, the same types of galaxies, the same cosmic architecture likely extend far beyond our view. Scientists use mathematical models to extrapolate these patterns. They can estimate how much additional universe probably exists beyond the observable boundary. Current estimates suggest the total universe is at least 400 times larger than the portion we can see. But this might be a conservative guess. The universe could extend infinitely in all directions, filled with countless copies of the cosmic structures we observe within our limited horizon. No matter how advanced our technology becomes, we cannot overcome the fundamental limits that create cosmic horizons. The speed of light represents an absolute barrier that no machine can break. Some people imagine that future spacecraft might travel faster than light, allowing us to explore beyond our current boundaries. But this violates the basic structure of space and time itself. Einstein's relativity shows that space and time are woven together into a single fabric. Moving faster than light would require breaking this fabric, essentially destroying the universe's fundamental architecture. Even if we could somehow exceed light speed, it wouldn't help us observe distant regions as they exist right now. We'd still be limited by the age of the universe and the finite time light has had to travel. The cosmic horizons represent permanent boundaries of knowledge. No future civilization, no matter how technologically advanced, will ever observe regions whose light has not had time to complete the journey across space. Cosmic horizons create the most fundamental limit to knowledge in the entire universe. They represent boundaries that cannot be crossed by any form of information. Beyond these horizons lie events, objects, and entire regions of space that remain forever unknowable, not because we lack the right instruments, but because the universe's structure makes this information fundamentally inaccessible. This creates what scientists call the information horizon problem. There are questions about the cosmos that have definite answers, but those answers exist beyond our reach. The existence of these absolute boundaries challenges our understanding of knowledge itself. Throughout human history, technological advances have pushed back the frontiers of the unknown, but cosmic horizons represent frontiers that can never be crossed. This limitation forces us to accept that our picture of the universe will always be incomplete. We can see only a finite sample of cosmic reality, isolated within our bubble of visibility. Everything beyond represents an eternal mystery that will persist as long as the universe continues to expand and evolve. In the 1990s, astronomers made measurements that shocked the scientific world. They studied distant exploding stars called supernovas. These cosmic explosions should have appeared brighter than they actually did. Supernovas work like cosmic lighthouses. They explode with predictable brightness, allowing scientists to calculate their distance. When astronomers measured supernovas in distant galaxies, something was wrong. The stars appeared dimmer than expected. This could only mean one thing: they were farther away than calculations predicted. Scientists call these exploding stars type A supernovas. They occur when a white dwarf star accumulates too much material and detonates. Each explosion releases roughly the same amount of energy, making them perfect cosmic measuring tools. The dimness revealed that universal expansion wasn't slowing down as everyone expected. Instead, it was speeding up. The space between galaxies was growing faster and faster, pushing these distant explosions farther away than gravity alone could explain. Dark energy doesn't clump together like ordinary matter. It spreads uniformly throughout every corner of the universe, creating a constant pressure that pushes space apart. Unlike gravity, which pulls things together, dark energy acts like anti-gravity. It generates a repulsive force that becomes stronger as space expands. The more space exists, the more dark energy fills it. Scientists estimate that dark energy makes up about 70% of everything in the universe, but it's completely invisible and doesn't interact with light or ordinary matter in any detectable way. This uniform distribution means dark energy affects every region of space equally. It doesn't form clumps or structures like galaxies do. Instead, it permeates the cosmic vacuum itself. The anti-gravity effect of dark energy only becomes noticeable over enormous distances. Within our solar system or even our galaxy, gravity overwhelms dark energy's influence. But on cosmic scales, dark energy dominates everything, driving the accelerated expansion that will ultimately determine the universe's fate. physicists have calculated how much dark energy should exist based on quantum mechanics. Their answer is spectacularly wrong, off by more than a factor of 10 to the power of 120. This represents the worst prediction in the history of science. Imagine trying to predict someone's weight and being off by more than all the atoms in the observable universe combined. Scientists call this the cosmological constant problem. The amount of dark energy that quantum theory predicts would instantly tear apart every atom in existence. Yet observations clearly show that dark energy exists and has a very specific, much smaller value. This discrepancy reveals a fundamental gap in our understanding of reality. No current theory can explain why dark energy has exactly the right strength to accelerate cosmic expansion without destroying everything. This mismatch between prediction and observation represents modern physics' greatest unsolved puzzle, suggesting that something profound about the universe's basic nature remains hidden from our understanding. For most of cosmic history, ordinary matter controlled the universe's expansion. Gravity from stars, galaxies, and dark matter dominated cosmic evolution. Then everything changed. About 5 billion years ago, dark energy's density surpassed matter's density. This marked a fundamental shift in cosmic power. From that moment forward, dark energy began driving universal expansion. The density reversal happened gradually. As space expanded, matter got spread thinner and thinner. But dark energy maintained constant density throughout the growing volume. This takeover determines the universe's future. Matter and gravity can no longer slow down cosmic expansion. Dark energy now controls the cosmic steering wheel. The universe entered a new phase of existence where expansion accelerates rather than decelerates. This shift from matter-dominated to dark energy-dominated cosmos represents the most significant transition since the Big Bang itself, fundamentally altering the trajectory of everything that exists. There's a specific distance in the universe where something remarkable happens. Galaxies beyond this boundary move away from us faster than light can travel. This doesn't violate Einstein's relativity because the galaxies themselves aren't moving through space faster than light. Instead, space itself expands so rapidly that it carries distant galaxies away at super-light speeds. Scientists call this boundary the Hubble sphere. Currently, it sits about 14 billion light-years away. Any galaxy beyond this distance recedes faster than light speed. Once a galaxy crosses this boundary, we lose all possibility of future contact. Even if we sent a light signal today, it would never catch up to these rapidly receding objects. This creates permanent cosmic isolation. Galaxies beyond the critical distance become forever unreachable, no matter how long we wait or how fast we try to send signals. The accelerating expansion ensures that this separation zone grows larger every day, swallowing more distant galaxies into eternal disconnection. In the far future, the universe will enter a phase called exponential expansion. Space will grow at an ever-increasing rate, doubling in size at regular intervals. This type of expansion creates permanent event horizons around every observer. These boundaries mark the limits of regions that can ever be reached or influenced. Scientists call this future state de Sitter space, named after the physicist who first described it. In de Sitter space, every galaxy becomes isolated within its own cosmic bubble. The exponential expansion means that space grows faster than light can cross it. This permanently cuts off communication between distant regions of the universe. Unlike today's expanding universe, where distant objects slowly fade from view, exponential expansion creates hard boundaries that can never be crossed. Each cosmic island becomes completely isolated from all others, surrounded by space that grows too quickly for any signal to traverse. Scientists have considered a terrifying possibility. What if dark energy grows stronger over time, instead of remaining constant? This hypothetical scenario involves phantom dark energy, a version that becomes more powerful as the universe ages. If this type of dark energy exists, it would eventually overcome every force in nature. The phantom energy would first separate galaxy clusters. Then it would tear apart individual galaxies. Next, it would rip apart solar systems and planets. In the final moments, phantom energy would overcome the forces holding atoms together. Every particle in the universe would be torn apart in an event scientists call the Big Rip. Current observations suggest that dark energy remains relatively constant over time. But if phantom dark energy exists, it would end the universe not with a whimper, but with the ultimate cosmic destruction, shredding the very fabric of reality itself in a final crescendo of accelerating expansion. The universe has a perfectly flat geometry. This means that parallel lines stay parallel forever, and the angles of triangles add up to exactly 180 degrees. Maintaining flat geometry requires a precise balance between matter, energy, and the expansion rate. Too much matter would curve space inward. Too little would curve it outward. Dark energy provides exactly the right amount of repulsive pressure to keep space perfectly flat. It counteracts the curvature that matter and radiation would otherwise create. Scientists call this the flatness problem. The universe's geometry must be incredibly fine-tuned to remain flat over billions of years of expansion. Dark energy solves this puzzle by providing a cosmic balancing force. Its anti-gravity effect exactly cancels the gravitational curvature from all other forms of matter and energy, maintaining the universe's geometric perfection throughout its entire history. Dark energy might be the strangest thing in the universe. Scientists know it exists because they can measure its effects, but they have absolutely no idea what it actually is. The leading candidate is vacuum energy, the idea that empty space itself contains energy. Quantum mechanics suggests that even pure vacuum bubbles with activity from virtual particles can exist. Another possibility involves new types of energy fields that permeate space. These hypothetical fields would be completely unlike any form of matter or energy we've ever encountered. Some scientists speculate that dark energy represents a fundamental property of space itself. Perhaps the vacuum has an intrinsic tendency to expand, built into the basic structure of reality. The truth is that dark energy remains one of the deepest mysteries in all of science. We can measure its effects with extraordinary precision, but its fundamental nature continues to elude our understanding, representing a profound gap in human knowledge about the cosmos. If dark energy continues driving accelerated expansion forever, the universe faces a bleak future known as heat death. As space expands, everything becomes more and more diluted. Galaxies spread apart until they disappear beyond each other's horizons. Stars exhaust their fuel and burn out. Eventually, even black holes evaporate through Hawking radiation. The universe becomes filled with nothing but elementary particles scattered across vast, cold expanses of space. Heat death occurs when the universe reaches maximum entropy, a state where no energy differences exist to drive any processes. Everything reaches the same temperature, just above absolute zero. This represents the ultimate triumph of dark energy over all other forces. By continuously stretching space, dark energy dilutes and separates everything until no organized structures can persist, leaving behind only a cold, dark, empty cosmos drifting toward eternal stagnation. Scientists worldwide are conducting sophisticated observations to understand how dark energy might change over time. These measurements will determine the universe's ultimate fate. Current telescopes study distant supernovas, galaxy clusters, and cosmic background radiation to track dark energy strength throughout cosmic history. The key question is whether dark energy remains constant or evolves. If it stays the same, the universe will expand forever. If it grows stronger, we might face the Big Rip. If it weakens, expansion could eventually reverse. Scientists use something called the equation of state to describe dark energy's behavior. This mathematical relationship reveals how dark energy's pressure relates to its density. These observations represent humanity's attempt to predict the ultimate destiny of everything that exists. By measuring dark energy's properties with ever greater precision, scientists hope to unveil whether the universe faces eternal expansion, catastrophic destruction, or some other cosmic finale. Dark energy doesn't just push galaxies apart. It actively prevents new cosmic structures from forming. This effect will ultimately sterilize the universe of organized matter. In the early universe, gravity could pull matter together to form galaxies, stars, and planets. But as dark energy gains strength, it overwhelms gravity's ability to create new structures. Future galaxy formation has essentially stopped. The matter needed to build new galaxies is being stretched too thin by accelerated expansion. Star formation will also cease as galaxies exhaust their gas supplies. Dark energy prevents fresh material from accumulating in star-forming regions. This structural suppression means the universe has already seen its golden age of cosmic construction. From now on, dark energy will systematically dismantle the organized structures that gravity spent billions of years building, leaving behind an increasingly empty and sterile cosmos. There's an invisible boundary in space that cuts off all future communication. Cross this line, and your signals can never reach their destination, no matter how long you wait. Scientists call this boundary the event horizon. It's completely different from the observable universe boundary. The observable universe shows us what we can see from the past. The event horizon determines what we can influence in the future. This boundary exists because space expands faster than light can travel across it. When you send a signal toward a distant galaxy, space grows while your message travels through it. If the galaxy lies beyond the event horizon, space expands so rapidly that your signal never catches up. It's like trying to swim upstream in a river that flows faster than you can swim. The event horizon creates permanent cosmic isolation. Galaxies beyond this boundary become forever unreachable, no matter how powerful our transmitters become or how patient we are. This represents the ultimate limit of causal influence in an expanding universe. How far away is a distant galaxy? In an expanding universe, this simple question has no simple answer. Distance becomes a confusing concept with multiple definitions. Consider a galaxy whose light takes 10 billion years to reach us. We could measure the distance light actually traveled, about 10 billion light years. But that's not where the galaxy is now. We could measure where the galaxy was when it emitted the light we see today. This moving distance accounts for how much closer everything was in the past due to universal expansion. Or we could calculate where that galaxy is right now, accounting for 10 billion years of space expansion while its light traveled to us. This current distance might be 20 billion light years or more. Scientists use different distance measures for different purposes. Light travel distance tells us about the past. Comoving distance helps with cosmic geometry. Current distance reveals present-day locations. Each measurement gives different numbers for the same galaxy, creating fundamental confusion about what distance even means. Light from galaxies approaching the event horizon undergoes a strange transformation. The expansion of space stretches these light waves until they vanish completely. As space expands, light waves get stretched along with it. This stretching shifts light toward redder and redder wavelengths, a process called cosmological redshift. For galaxies near the event horizon, this redshift becomes extreme. Their light gets stretched so much that it shifts beyond infrared, beyond radio waves, into wavelengths we cannot detect. At the exact event horizon boundary, redshift becomes infinite. Light waves get stretched to infinite wavelength, effectively disappearing from the universe. This creates a cosmic fade-out effect. Galaxies don't suddenly vanish. They slowly fade to red, then infrared, then radio waves, then nothing. The event horizon acts like a one-way filter that gradually erases all signals from the most distant regions of space. Right now, as you listen to this, some galaxies we can observe have already crossed beyond the event horizon. We can still see them, but we can never communicate with them again. This creates a strange cosmic situation. Light from these galaxies continues to reach us, showing us their ancient history. But any signal we send today will never arrive at their current location. The galaxies haven't disappeared from view yet because we're still receiving light they emitted billions of years ago when they were much closer to us. These galaxies exist in a communication twilight zone. We remain connected to their past through the light we receive, but disconnected from their future through the impossibility of signal transmission. Current estimates suggest that roughly half of the galaxies we can observe tonight have already passed beyond our causal reach. We're witnessing their ancient light while being forever cut off from their present reality. Universal expansion doesn't just move galaxies apart. It fundamentally limits how different regions of space can influence each other. Information cannot travel faster than light, and space expansion can outrun light itself. This creates what scientists call causal limitations. Cause and effect relationships require information transfer, which requires signals that can actually complete their journey. When space expands faster than light can cross it, causal connections get severed. Events in one region cannot influence events in another region if the space between them grows too quickly. The expansion rate determines the maximum size of causally connected regions. Areas of space that expand too rapidly lose the ability to exchange information and coordinate their behavior. This represents a fundamental constraint on cosmic organization. Universal expansion doesn't just separate matter. It severs the information connections that allow different parts of the universe to respond to each other, creating isolated cosmic regions that evolve independently. The universe has two completely different horizons that work in opposite directions. One controls what we can see from the past. The other controls where we can send signals in the future. The particle horizon, also called the cosmic light horizon, marks the boundary of regions whose light has had time to reach us. Beyond this boundary, we cannot see anything because light hasn't had enough time to complete the journey. The event horizon marks the boundary of regions we can still influence with signals sent today. Beyond this boundary, our messages will never arrive, no matter how long we wait. These two horizons have different sizes and positions. Some galaxies lie within our particle horizon, so we can see them, but beyond our event horizon, so we can never reach them. This asymmetry creates a fundamental difference between observation and communication. The universe allows us to receive information from regions we can never influence, creating a permanent separation between cosmic knowledge and cosmic action. The event horizon isn't fixed in space. As universal expansion accelerates, this boundary actually moves closer to us, shrinking the region we can influence. Each day, galaxies that were previously reachable slip beyond our causal boundary. The cosmic neighborhood we can communicate with grows smaller and smaller. This process will continue indefinitely. Accelerating expansion means the event horizon contracts toward our local region, eventually isolating us with only our immediate galactic neighbors. In the far future, our event horizon will shrink to include only the local group, our galaxy, Andromeda, and a few smaller companions. Everything else will lie beyond our causal reach. The shrinking event horizon represents the gradual cosmic isolation of every observer in the universe. Each region becomes progressively more cut off from all others, creating a cosmos divided into causally disconnected islands. Quantum entanglement allows particles to instantaneously influence each other across vast distances. Einstein called this spooky action at a distance. But even this mysterious connection cannot cross cosmic event horizons. When two particles are quantum entangled, measuring one instantly affects the other, regardless of the distance between them. This seems to violate the speed of light limit. However, entanglement cannot transmit usable information faster than light. It only correlates the random outcomes of measurements on both particles. More importantly, cosmic expansion can separate entangled particles beyond the event horizon. Once this happens, the entanglement connection gets permanently severed. This reveals that event horizons represent absolute barriers to all forms of correlation and influence. Even quantum mechanics' strangest phenomena cannot overcome the causal limitations imposed by accelerating cosmic expansion. When galaxies slip beyond the event horizon, they don't just become unreachable. All information about their current state gets permanently erased from our region of the universe. We can still see their ancient light showing us how they appeared billions of years ago. But their present condition, their current evolution, their ongoing history becomes forever unknowable. This creates genuine information loss. Entire chapters of cosmic history get deleted from our accessible reality, not just hidden or delayed. Consider a galaxy that crosses our event horizon today. Billions of years from now, when its last ancient light finally reaches us, that galaxy's entire existence will effectively end from our perspective. The information loss is absolute and irreversible. No future technology, no matter how advanced, can recover knowledge about post-horizon events in these lost galaxies. Cosmic expansion literally deletes parts of reality from our accessible universe. Black holes and the cosmic event horizon share remarkable similarities. Both create boundaries where information cannot escape and where time appears to slow down. Just as nothing can escape from inside a black hole's event horizon, nothing can return from beyond the cosmic event horizon. Both represent permanent one-way boundaries in space-time. Time dilation effects occur at both types of horizons. Near a black hole's event horizon, time slows down dramatically. Near the cosmic event horizon, redshift creates a similar time-slowing effect. Both horizons encode information on their surfaces according to the holographic principle. The information about what crosses these boundaries gets stored in a two-dimensional form on the boundary itself. This connection suggests that event horizons represent a fundamental feature of spacetime geometry. Whether created by massive objects or cosmic expansion, these boundaries impose similar limitations on information and causality throughout the universe. The universe is fragmenting into causally disconnected islands. As event horizons shrink, each region becomes permanently isolated from all others. Each cosmic island will contain a local group of galaxies bound together by gravity. These islands will evolve independently, with no possibility of information exchange between them. The boundaries between islands are event horizons. Once formed, these boundaries become permanent and insurmountable, dividing the universe into separate realms of existence. Within each island, physics and causality operate normally. Between islands, no communication or influence remains possible. Each region essentially becomes its own separate universe. This cosmic archipelago represents the ultimate fate of an accelerating universe. Instead of one connected cosmos, we end up with countless isolated regions, each containing a small collection of galaxies surrounded by ever-expanding empty space that prevents any contact with neighboring islands. Our local group of galaxies behaves differently from the rest of the universe. While distant galaxies race away from us, our immediate neighbors move toward us instead. Gravity holds our local cosmic neighborhood together. The local group contains about 80 galaxies, including our Milky Way, the Andromeda Galaxy, and dozens of smaller companions. Within this gravitationally bound region, universal expansion has no effect. The galaxies orbit around their common center of mass, just like planets orbit the Sun. Scientists call this a gravitationally bound system. It means the attractive force of gravity overpowers the repulsive force of cosmic expansion. The local group spans about 10 million light-years across. Within this volume, gravity wins the cosmic tug-of-war against dark energy. Our galactic neighborhood remains intact while the rest of the universe expands around us, creating a stable island of connected galaxies in an ocean of cosmic separation. At the boundary of large galaxy clusters, cosmic expansion and gravity engage in an epic battle. The outcome determines which galaxies stay connected and which ones get swept away forever. The Virgo cluster sits at this cosmic battleground. It's the nearest large collection of galaxies to our local group, containing over 1,300 individual galaxies. Some galaxies on the cluster's edge feel almost equal pull from both forces. Gravity tries to drag them into the cluster. Expansion tries to carry them away into space. This creates what scientists call the turnaround radius. Inside this boundary, gravity dominates and galaxies fall toward the cluster center. Outside this boundary, expansion dominates and galaxies flee into the cosmic void. The competition creates a delicate equilibrium zone where galaxies hover between cosmic destinations. Their ultimate fate depends on tiny differences in gravitational pull and expansion rate, making the cluster edge a dynamic frontier in the ongoing cosmic war. There's a specific distance from Earth where gravity loses its ability to hold galaxies together permanently. Beyond this critical boundary, even the strongest gravitational attractions cannot prevent cosmic separation. Galaxies beyond roughly 100 million light-years from us experience expansion effects that overpower local gravitational interactions. At these distances, space expands fast enough to overcome the gravitational bonds between galaxies. Even massive galaxy clusters start to feel the stretching effects of dark energy. The critical distance acts like a cosmic watershed. Galaxies closer than this boundary can potentially remain gravitationally connected to us. Galaxies farther away will eventually be swept beyond our reach by accelerating expansion. This boundary isn't fixed. It slowly shrinks over time as dark energy grows stronger. More and more galaxies cross from the gravitationally connected realm into the expansion-dominated realm, where they begin their permanent journey away from our cosmic neighborhood. In the far future, our cosmic view will become incredibly lonely. Nearly every galaxy we see today will disappear beyond the cosmic horizon, leaving us with only our immediate galactic family. The local group will survive as an isolated island. Our Milky Way Andromeda and their small companion galaxies will remain gravitationally bound together. But everything else will vanish. The Virgo cluster, distant galaxy clusters, and individual galaxies scattered throughout space will all disappear from view. Future astronomers living trillions of years from now will see a universe that appears almost empty. They'll observe perhaps 100 nearby galaxies surrounded by infinite darkness. This cosmic loneliness represents the ultimate victory of dark energy over gravity. Accelerating expansion will separate our local group from all other structures in the universe, creating a small island of connected galaxies floating in a vast ocean of empty, ever-expanding space. The largest structures in the universe are beginning to fall apart. Galaxy clusters, superclusters, and cosmic filaments face gradual dissolution as expansion weakens their gravitational connections. These cosmic structures formed when the universe was younger and denser. Back then, matter was packed closely enough for gravity to pull vast regions together into organized patterns. As space expands, the matter within these structures gets stretched thinner and thinner. The gravitational glue holding them together gradually weakens. Large-scale structure dissolution happens slowly. First, the connections between distant superclusters break. Then individual superclusters fragment. Finally, even galaxy clusters start to disperse. This represents a fundamental phase transition in cosmic evolution. The universe is shifting from an era of structure formation to an era of structure dissolution, where expansion systematically dismantles the cosmic architecture that gravity spent billions of years constructing. Dark energy doesn't destroy cosmic structures all at once. Instead, it follows a systematic pattern, dismantling the universe's architecture in order from largest to smallest. First, the connections between galaxy superclusters break apart. These represent the largest gravitationally bound structures, so they're the most vulnerable to expansion effects. Next, individual superclusters fragment into their component galaxy clusters. The clusters themselves initially remain intact, but lose their connections to neighboring clusters. Then galaxy clusters begin to dissolve. Member galaxies gradually drift away from the cluster center as expansion overcomes the cluster's collective gravitational pull. Eventually, even smaller galaxy groups like our local group may face dissolution, though this won't happen for many trillions of years. The hierarchical breakdown ensures that cosmic loneliness increases gradually, starting with the loss of the most distant connections and slowly working inward toward our immediate neighborhood. As galaxies move away from us faster and faster, their light gets stretched to such extreme wavelengths that we can no longer detect it. This stretching effect, called cosmological redshift, shifts light toward longer and longer wavelengths. Visible light becomes infrared. Infrared becomes radio waves. Radio waves become undetectable. Galaxies near the edge of the observable universe already show extreme redshift. Their light has been stretched so much that it barely registers on our most sensitive instruments. As expansion accelerates, this redshift becomes more and more severe for distant objects. Galaxies don't suddenly disappear. They slowly fade through the electromagnetic spectrum until they vanish completely. The extreme redshift creates a cosmic dimming effect that gradually erases distant galaxies from our view, even if these galaxies continue to exist and shine brightly. Their light becomes so stretched by space expansion that it effectively disappears, leaving us with an increasingly empty-looking universe. Our cosmic horizon, the boundary of what we can observe, isn't fixed in space. As expansion accelerates, this boundary actually shrinks, hiding more and more galaxies from our view. The shrinking happens because accelerating expansion makes it harder for light from distant regions to reach us. Galaxies that are currently visible will eventually slip beyond our observational reach. Each billion years that pass, fewer galaxies remain visible from Earth. The cosmic horizon contracts like a slowly closing curtain, gradually blocking our view of distant cosmic regions. This process affects our count of observable galaxies. Current surveys catalog billions of galaxies throughout the visible universe. But future surveys will find fewer and fewer objects as the horizon contracts. The shrinking horizon represents a fundamental loss of cosmic information. Galaxies don't cease to exist, they simply disappear from our accessible universe, creating an observational horizon that progressively limits our knowledge of the cosmos. Gravitational waves from distant cosmic events suffer the same fate as light. Space expansion stretches these ripples in spacetime until they become undetectable. When massive objects like black holes collide, they create gravitational waves that travel through space at light speed. These waves carry information about cosmic events across vast distances. But expansion stretches gravitational waves just like it stretches light waves. The waves get longer and weaker as they travel through expanding space. Gravitational waves from the most distant cosmic events get stretched to wavelengths larger than entire galaxies. At this point, they become impossible to detect with any conceivable instrument. This means we're losing our ability to detect gravitational signals from distant regions of the universe. As expansion accelerates, fewer and fewer cosmic events will produce gravitational waves strong enough to reach our detectors, gradually cutting us off from this important source of cosmic information. Scientists living in the far future will face a cosmic mystery that seems impossible to solve. They'll observe a nearly empty universe and conclude that galaxies are incredibly rare. Future astronomers will see only the local group galaxies in their night sky. Everything else will have disappeared beyond the cosmic horizon or faded beyond detection. Without knowledge of cosmic history, these future scientists might conclude that the universe contains only a few dozen galaxies scattered through mostly empty space. They'll miss the evidence for universal expansion, dark energy, and the Big Bang. The cosmic microwave background will have cooled and redshifted beyond detection. Distant galaxies will have vanished from view. This astronomical blindness represents one of expansion's most profound effects. The very evidence that allowed us to discover the universe's true nature will gradually disappear, leaving future civilizations with a misleading picture of cosmic reality that makes the universe appear much smaller and simpler than it actually is. Fewer and fewer stars are being born each year. The universe's star formation rate has been declining for billions of years, and this cosmic baby boom is winding down permanently. In the early universe, gas clouds collapsed rapidly to form new stars. Massive star-forming regions blazed with the light of millions of newborn suns. But star formation requires specific conditions. Gas must be dense enough and cool enough to collapse under its own gravity. These ideal conditions are becoming increasingly rare. The peak of star formation occurred about 10 billion years ago, when the universe was much younger and denser. Since then, the rate has steadily declined. Current observations show that star formation happens about 10 times slower today than during the cosmic peak. This isn't a temporary decline. It's a permanent transition toward a universe where new stars rarely form, leaving the cosmos to slowly burn through its existing stellar population. The raw materials for making stars are running out. Gas and dust, the essential ingredients for stellar birth, get spread thinner and thinner as space expands. Stars form when giant clouds of hydrogen gas collapse under gravity. These stellar nurseries need dense concentrations of material to trigger the collapse process. But cosmic expansion dilutes these gas clouds. As space grows larger, the same amount of material gets spread across a much larger volume. This dilution effect makes it harder and harder for gas clouds to reach the critical density needed for star formation. The material is still there, but it's too spread out to collapse effectively. Eventually, expansion will dilute star-forming materials so much that new star birth becomes virtually impossible. The universe will enter a permanent drought of stellar creation, forced to rely on the existing population of stars that will slowly burn out over trillions of years. When almost everything else in the universe has died, one type of star will still be shining. Red dwarf stars burn so slowly and efficiently that they can survive for trillions of years. Red dwarfs are much smaller than our Sun, sometimes less than 1/10 the mass. This tiny size makes them incredibly efficient with their nuclear fuel. While massive stars burn through their fuel in millions of years, red dwarfs sip their hydrogen so slowly that they can shine for longer than the current age of the universe. Multiplied by 1,000. These stellar survivors will provide the universe's last sources of light and warmth. Long after our Sun has died, long after massive stars have exploded or collapsed, red dwarfs will continue their slow burn. In the far future, red dwarf stars will be the only remaining beacons in an increasingly dark and cold cosmos, providing tiny islands of energy in a universe that has otherwise exhausted its ability to generate new light. White dwarf stars are cosmic embers that take an almost unimaginable amount of time to cool off completely. These stellar remnants will glow faintly for quadrillions of years after their parent stars have died. When medium-sized stars like our Sun exhaust their nuclear fuel, they shed their outer layers and leave behind a hot, dense core called a white dwarf. White dwarfs start out incredibly hot, surface temperatures reaching 100,000 degrees. But they have no internal energy source, so they can only cool down by radiating heat away. The cooling process happens extremely slowly because white dwarfs are so dense that they hold on to their heat very efficiently. Think of them as cosmic space heaters that take forever to cool off. Current calculations suggest it takes over a quadrillion years for a white dwarf to cool down to the same temperature as the cosmic background radiation. This means white dwarf stars will be among the last warm objects in a universe that slowly approaches absolute zero. Some physicists believe that even atoms aren't permanent. If certain theories are correct, protons, the building blocks of all atomic nuclei, will eventually decay and disappear. Protons seem incredibly stable. In all of human observation, we've never seen a single proton decay naturally. But some theories of particle physics predict that protons have an extremely long but finite lifetime. The predicted proton lifetime is staggeringly long, possibly 10 to the 34th years. That's far longer than the current age of the universe multiplied by itself many times over. If proton decay occurs, it would gradually dissolve all ordinary matter. Stars, planets, and everything made of atoms would slowly disintegrate as their protons randomly decay into lighter particles. This process would unfold so slowly that it wouldn't affect anything for unimaginably long periods. But eventually, if the theories are correct, every atom in the universe would break apart, leaving behind only a thin soup of elementary particles and radiation. Black holes will be the last massive objects to survive in the universe. But even these cosmic giants aren't eternal. They slowly evaporate through a quantum process discovered by Stephen Hawking. Hawking radiation occurs when quantum effects near a black hole's event horizon cause it to emit particles. This process makes black holes gradually lose mass and shrink. The evaporation rate depends on the black hole's size. Smaller black holes evaporate faster than larger ones. Stellar mass black holes take about 10 to the 67th years to completely evaporate. Supermassive black holes at galaxy centers take even longer, possibly 10 to the 100th years or more. These cosmic timeframes dwarf all previous cosmic events. Eventually, even the largest black holes will evaporate completely, leaving behind only a faint burst of radiation. This represents the final elimination of the last organized structures in the universe, marking the end of the black hole era and the beginning of an epoch where only elementary particles remain. The universe is getting colder and colder, approaching a final temperature just barely above absolute zero. This cosmic cooling represents the ultimate victory of expansion over all sources of heat. As space expands, it stretches radiation and causes temperatures to drop. The cosmic microwave background, which started hot enough to vaporize any material, has already cooled to just a few degrees above absolute zero. All heat sources in the universe are temporary. Stars burn out, black holes evaporate. Planetary cores solidify. Eventually, no significant sources of energy remain to warm anything. The final temperature will be determined by the faintest remaining radiation in the universe. Current estimates suggest the cosmos will asymptotically approach a temperature of about a 10 trillionth of a degree above absolute zero. At this ultimate temperature, virtually all thermal motion ceases, atoms barely vibrate, chemical reactions become impossible. The universe enters a state of maximum cold where nothing can generate or maintain warmth against the relentless cooling effect of eternal expansion. The universe is evolving toward a state of maximum entropy, a condition where no energy differences exist to drive any processes or create any changes. Entropy measures disorder and randomness. The second law of thermodynamics states that entropy always increases over time. Hot objects cool down, organized structures break apart, energy spreads out evenly. Eventually, the universe will reach thermal equilibrium. All regions will have exactly the same temperature. All energy will be distributed uniformly throughout space. In this maximum entropy state, no work can be performed. No machines can operate. No life processes can function. Everything reaches the same energy level. Scientists call this final state heat death, not because everything becomes hot, but because heat can no longer flow between regions. With no energy gradients remaining to drive any processes, the universe enters a permanent state of stagnation where nothing significant can ever happen again. In the ultimate future, the universe becomes almost perfectly empty. But even in this void, quantum mechanics ensures that space never becomes completely lifeless. Quantum uncertainty means that empty space constantly bubbles with virtual particle creation. Pairs of particles spontaneously appear and then immediately annihilate each other. These virtual particles exist for incredibly brief moments, usually much less than a trillionth of a second. They borrow energy from the quantum vacuum to exist temporarily, then return that energy when they disappear. The virtual particle activity represents the only remaining events in a universe that has otherwise reached maximum entropy and thermal equilibrium. Even this minimal quantum activity occurs at an incredibly low rate. Virtual particle pairs pop into existence so rarely and briefly that the universe appears essentially dead, punctuated only by the occasional flicker of ephemeral quantum ghosts in an otherwise empty and changeless cosmos. All information about the universe's rich history will eventually be erased forever. The expansion and cooling of space gradually dilutes every trace of past events until none remain. Information in the universe exists in many forms. The arrangement of atoms, the patterns of radiation, the distribution of matter, all carry records of cosmic events. But expansion spreads this information across ever larger volumes. Cooling reduces the energy available to maintain organized patterns. Entropy increases randomness and destroys correlations. Eventually, all historical information gets so diluted and randomized that it becomes unrecoverable. No trace remains of galaxy formation, star birth, planet evolution, or any other cosmic event. This information erasure is absolute and irreversible. Future civilizations, if they could somehow exist, would have no way to reconstruct the universe's past. Every record of the cosmos's rich 13-billion-year history disappears into the fog of maximum entropy and thermal equilibrium. The universe's final destination is a state called heat death, where perfect uniformity eliminates all possibility of change or activity. Heat death occurs when the universe reaches thermal equilibrium. Every region has exactly the same temperature, pressure, and density. No energy flows between different areas. Without energy differences, no processes can operate. Heat engines need temperature differences to function. Life requires energy gradients to maintain organization against entropy. In the heat death state, the universe becomes perfectly smooth and featureless. No stars, no planets, no structure of any kind, just a uniform distribution of elementary particles at the same temperature. This represents the complete elimination of all driving forces for change. With no energy gradients remaining anywhere in the cosmos, nothing can ever happen to disturb the perfect equilibrium. The universe reaches a final state of absolute stagnation that persists forever. What happens after heat death? Science reaches its limits when trying to predict the infinite future of a universe in thermal equilibrium. Some physicists speculate about quantum tunneling events that might create new regions of space with different physical laws. Others suggest that vacuum decay could transform the entire cosmos. Random quantum fluctuations might occasionally create small pockets of order in the vast thermal equilibrium. Given infinite time, even incredibly unlikely events could eventually occur. But these possibilities remain pure speculation. The timeframes involved are so vast that they exceed our ability to make meaningful predictions. The infinite future of our universe represents the ultimate boundary of scientific knowledge. We can trace cosmic evolution from the Big Bang through star formation, galaxy evolution, and eventual heat death, but beyond that point lies an eternal mystery that may forever remain beyond human understanding. Every photon of starlight acts like a cosmic time traveler carrying messages from the past. When you look up at the night sky, You're literally seeing ancient history playing out in real time. The light from distant stars and galaxies left those objects millions or billions of years ago. It has been racing through space ever since, carrying a perfect record of how those cosmic objects appeared when the light began its journey. This creates a natural time machine effect. The farther away an object is, the further back in time we see it. Distant galaxies show us what the universe looked like when it was young. Scientists call this the look-back time effect. Light preserves cosmic history by freezing moments in time and delivering them to us across vast distances. The preservation isn't perfect, though. Only the information that light can carry survives the journey. Everything else about those ancient cosmic moments gets lost forever, creating an incomplete but precious record of the universe's past that exists only in the starlight still traveling toward us. Nothing in the universe can carry information faster than the speed of light. This isn't just a technological limitation. It's a fundamental law of physics that governs all communication and knowledge transfer. Light travels at about 300 million meters per second in empty space. This seems incredibly fast by human standards, but on cosmic scales it creates significant delays. Information includes everything from radio signals to gravitational waves to the simple fact that something exists at a particular location. All these forms of information must respect the cosmic speed limit. The speed limit creates what scientists call the information horizon. Beyond a certain distance, information simply hasn't had time to travel from distant regions of space to reach us. This fundamental constraint means the universe has built-in delays and barriers to knowledge. No matter how advanced our technology becomes, we cannot receive information from events happening right now in distant galaxies. We must wait for that information to complete its journey across space at the speed of light. What happens to information when it crosses an event horizon? It doesn't get destroyed. It gets permanently locked away in a cosmic vault that can never be opened again. Event horizons act like one-way information barriers. Information can cross them going inward, but nothing can ever come back to tell us what happened beyond the boundary. This creates genuine information loss from our perspective. Entire galaxies carrying billions of years of cosmic history slip beyond event horizons and take all their information with them. The information isn't destroyed in any absolute sense. It still exists beyond the horizon, but it becomes completely inaccessible to us, as if it had been locked in a cosmic safe and the key thrown away. This represents a fundamental limitation on cosmic knowledge. There are events happening right now beyond various horizons that have definite outcomes, but we can never learn what those outcomes are, creating permanent gaps in our understanding of cosmic reality. One of the strangest discoveries in modern physics suggests that all the information in a three-dimensional region of space can be encoded on its two-dimensional boundary surface. Scientists call this the holographic principle. Just like a hologram stores a 3D image on a 2D surface, the universe might store all information about what happens inside any region on the boundary of that region. This principle applies to cosmic horizons. All the information about what crosses an event horizon gets encoded on the horizon surface itself, even though the original objects continue traveling into the interior. Think of it like a cosmic library where all the books get stored as writing on the library walls rather than on shelves inside. The information content remains the same, but it's stored in a completely different way. The holographic principle suggests that event horizons function as information storage devices, preserving perfect records of everything that crosses them, while making that information inaccessible to observers outside the horizon boundary. Quantum information behaves differently from ordinary information. When quantum systems get separated by cosmic expansion, their delicate information patterns break down and become unrecoverable. Quantum information depends on precise correlations between particles that can be incredibly fragile. These correlations can survive only when the particles remain in close contact with each other. Cosmic expansion stretches quantum systems apart and destroys the correlations that encode quantum information. Once these correlations break, the information cannot be recovered, even in principle. This happens gradually as particles drift apart due to expansion. The quantum information doesn't disappear instantly. It slowly degrades until it becomes completely scrambled. The breakdown creates a fundamental form of cosmic forgetting. Quantum information that took billions of years to develop gets irreversibly lost as expansion pulls quantum systems apart beyond the point where their correlations can survive. The universe has finite memory storage capacity. There's a maximum amount of information that any region of space can contain, creating cosmic memory banks that eventually fill up completely. This limit comes from the relationship between information and entropy. Each bit of information requires a minimum amount of energy and space to store it physically. As the universe evolves and expands, more and more information gets generated. New cosmic events create new information about the state and history of different regions. But the storage capacity of any region grows more slowly than the information being generated. Eventually, some old information may have to be lost or become inaccessible to make room for new information. This creates a cosmic version of limited hard drive space. The universe can't remember everything forever. It must selectively forget some information to accommodate new developments, creating inevitable gaps in the cosmic record. Cosmic expansion creates isolated regions that lose all contact with each other and begin developing completely independent histories. These cosmic islands form when the space between regions expands so fast that light cannot catch up. Once this happens, no information can flow between the regions in either direction. Each isolated region evolves according to its own local conditions, with no knowledge of what happens in other regions. They become separate cosmic experiments running in parallel. The isolation is permanent and complete. No future technology can restore communication between causally disconnected cosmic islands. This fragmentation means the universe doesn't have a single unified history anymore. Instead, it has countless independent histories developing simultaneously in isolation, creating a cosmic multiverse of separate storylines that can never be connected or compared. Even the most advanced possible civilizations face fundamental physical limits on how much information they can store and remember about cosmic history. Memory requires physical storage, and physical storage is limited by the laws of physics. There's a maximum information density that any material system can achieve. These limits apply to brains, computers, and any conceivable memory storage device. No matter how cleverly designed, every memory system hits fundamental physical barriers. The limits become especially severe for cosmic scale information. Remembering the complete quantum state of even a small region of space would require more storage capacity than exists in that region. This means perfect cosmic memory is physically impossible. Every observer, no matter how advanced, must forget some information in order to remember other information. creating inevitable blind spots in every possible perspective on cosmic history. Physics faces a fundamental paradox when information crosses cosmic horizons. The laws of physics say information must be conserved, but horizons make information permanently inaccessible. Information conservation is a basic principle of quantum mechanics. Information about the quantum state of any system should never be truly lost or destroyed. But cosmic horizons create situations where information becomes completely unreachable. When a galaxy crosses an event horizon, its quantum information appears to be lost from our perspective. This creates what scientists call the cosmic information paradox. Either information conservation is violated, or the information isn't really lost but stored somewhere we can't access. The paradox reveals deep tensions in our understanding of spacetime, information, and cosmic horizons. Current physics has not fully resolved the conflict between fundamental conservation laws and the apparent information loss created by expanding spacetime geometry. Future civilizations will never be able to reconstruct a complete picture of cosmic history, no matter how advanced their technology becomes. Too much information gets permanently lost through various mechanisms. Cosmic horizons hide information beyond reach. Quantum decoherence scrambles correlations. Expansion dilutes information density. Even if future scientists could access all remaining information in their cosmic neighborhood, they would still be missing vast amounts of data about regions beyond their horizon. The missing information isn't just temporarily hidden, it's permanently erased from their accessible universe. No amount of clever reconstruction techniques can recover what no longer exists in any form they can detect. This represents one of the most profound limitations on cosmic knowledge. The universe's own evolution systematically destroys the information needed to understand its complete history, ensuring that cosmic amnesia becomes increasingly severe over time. Spacetime itself carries information, and cosmic expansion dilutes this information until it becomes undetectable. Even the fabric of reality gradually forgets its own history. Information gets encoded in the curvature of spacetime, the distribution of matter and energy, and the correlations between different regions. All of these information carriers get stretched and diluted by expansion. As space grows larger, the same information gets spread across a much larger volume. This dilution effect reduces information density until it falls below any possible detection threshold. The process is gradual but relentless. Information that was once clearly encoded in spacetime geometry becomes fainter and fainter until it disappears into the background noise of quantum fluctuations. Eventually, cosmic expansion may erase all historical information encoded in spacetime itself. The universe's memory of its own past gets progressively diluted until no trace remains of the events that shaped cosmic evolution, leaving behind a cosmos that has forgotten its own origins and development.